The True Nature of Gravity, a Journey Through Spacetime. Welcome to an exploration that will fundamentally transform your perception of reality itself. Today, we're investigating gravity, the phenomenon that shapes every instant of your existence. It anchors you to the planet. It holds our atmosphere in place. It guides Earth's dance around the sun. It orchestrates the movements of galaxies stretching across billions of light years. And here's something that might completely reshape your understanding. Gravity is not what you've been told it is. It's not a force at all. It's something far more elegant and profoundly beautiful than that. Before we venture deeper, if this journey captivates you, hitting the like button or subscribing genuinely helps this channel thrive. It's a small gesture from your perspective, but it creates a significant impact here. Now let's embark on this voyage into understanding gravity's true identity. Questioning what you know. Think about your understanding of gravity. An object slips from your hand and descends, straightforward, correct? Throughout your childhood, you learned that Earth's gravitational pull draws objects downward, that gravity represents a force yanking you toward the ground, that solar gravity captures Earth in its orbital path. The vast majority accept this explanation. Educational institutions present it this way, and while it's not entirely incorrect, it's fundamentally incomplete. It resembles declaring Earth flat simply because the horizon appears level from where you stand. That perspective functions adequately for daily purposes, but it completely misses the deeper reality. Isaac Newton discovered gravity's mathematical principles in 1687 with his publication of the Philosophia Naturalis Principia Mathematica, commonly known simply as the Principia. This stands among history's most transformative scientific documents. Prior to Newton, explanations for falling objects and planetary motion consisted largely of philosophical speculation. Newton revolutionized everything. He demonstrated that identical principles governing an apple's descent from its branch also maintain the moon's orbit around Earth and Earth's orbit around the sun. This was revolutionary. People believed celestial mechanics and terrestrial physics operated under fundamentally different laws. Newton unified them through a single mathematical framework. Newton's universal law of gravitation declares that every mass in the universe attracts every other mass, with a force directly proportional to their masses multiplied together and inversely proportional to the square of their separation distance. Let me clarify this concept. Earth and you exert mutual attraction with substantial force because Earth possesses enormous mass. You and a pencil resting across the room similarly pull on each other, but so incredibly weakly you'd never perceive it. Just how weak are these forces? Consider this. If you attempted constructing a gravitational wave detector sensitive enough to register a single person walking past your laboratory, you'd need detector arms extending roughly the distance between the Sun and Saturn, approximately 10 billion kilometers or 6 billion miles. Anything shorter would see the signal completely overwhelmed by quantum fluctuations and thermal noise. This explains why you can sense the tiniest magnet's pull or receive a static shock from a doorknob, yet two humans standing 1 meter apart attract each other gravitationally with less force than the weight of a single bacterium. Gravity operates 39 orders of magnitude weaker than electromagnetism at everyday scales, one of physics' deepest unsolved mysteries, and we haven't even addressed the inverse square law. When you double the separation distance, the gravitational pull doesn't merely halve, it plummets to 1/4. Triple the distance and it crashes to 1/9. This mathematical relationship explains why gravity dominates exclusively when dealing with truly astronomical masses. Newton's equations functioned magnificently. They predicted planetary trajectories with remarkable precision. They accounted for ocean tides, water rising and falling due to lunar gravity tugging on Earth's oceans. They explained why planets orbiting farther from the Sun move more sluggishly through their paths. They enabled scientists to discover new planets by observing minute irregularities in known planetary orbits. That's precisely how Neptune's existence was confirmed. In 1846, astronomers recognized that Uranus wasn't traveling exactly as Newton's equations predicted. They calculated where an undiscovered planet must reside to generate those deviations. They aimed their telescopes at that precise location, and there was Neptune, positioned exactly where mathematics indicated it should be. For over 2 centuries, Newton's laws were regarded as gravity's definitive description. But subtle problems existed. The most celebrated was Mercury's orbit. Mercury travels in an ellipse that gradually rotates over time, a phenomenon called precession. Newton's equations predicted how much Mercury should precess based on gravitational influences from other planets. But observations didn't align. Mercury was precessing approximately 43 arc-seconds more per century than predicted. That's roughly 1/80th of a degree per 100 years. Incredibly minute, yet real and measurable. Scientists pursued explanations. Perhaps an undiscovered planet called Vulcan was pulling on Mercury. It didn't exist. Perhaps Newton's laws required modification. Nothing succeeded. The mystery persisted unsolved until 1915, when Albert Einstein published his General Theory of Relativity, Einstein's revolutionary insight. Einstein's insight was radical. Gravity isn't a force whatsoever. Instead, it represents a curvature of space-time itself. That probably sounds like incomprehensible jargon. Space-time curvature. What does that actually mean? Let me construct this explanation step by step, building from concepts you already grasp. First, consider space and time separately, the way we typically conceive them. Space represents the three-dimensional arena where objects exist and navigate. You can move forward and backward, left and right, up and down. Those constitute your three spatial dimensions. Time operates differently. It flows unidirectionally from past toward future. You experience events sequentially. You cannot reverse through time or leap forward arbitrarily. Space and time appear fundamentally distinct. Space represents where events occur. Time represents when they occur. But Einstein revealed that space and time aren't separate entities. They're interwoven into a single four-dimensional fabric called spacetime. Not merely a mathematical convenience, a description of physical reality itself. You cannot have space without time or time without space. They're aspects of the same fundamental thing. When you travel through space, you simultaneously travel through time. When time elapses, you're also navigating through space-time. Even sitting motionless in space, every occurrence in the universe happens at a specific location within space-time. Not just in space and time separately, but within space-time as a unified four-dimensional structure. Here's where things become fascinating. Space-time isn't rigid. It's flexible. It can warp and curve. And what causes this curvature? Mass and energy. Any object possessing mass or energy curves the space-time surrounding it. The more massive the object, the more dramatically it curves space-time. Earth curves space-time around itself. The Sun curves space-time far more because it's vastly more massive. Even you curve space-time a minuscule amount. Everything with mass or energy curves space-time to some degree. Envision space-time like a stretched rubber membrane. Place a bowling ball on that membrane and it creates a depression. The heavier the ball, the deeper the depression. Roll a marble near the bowling ball and the marble doesn't travel in a straight line. It curves toward the bowling ball following the slope of the depression. From the marble's perspective, it's simply following the straightest available path. But because the membrane is curved, that path bends toward the bowling ball. Similarly, Earth curves space-time around itself. When you drop an object, it isn't being pulled by a force. It's following the straightest possible path through curved space-time. That path happens to curve toward Earth's center. The analogy has limitations. The rubber membrane is a two-dimensional surface being bent within a third dimension, but space-time is four-dimensional and it's not bending into some higher dimension. It's intrinsically curved, meaning the curvature is a property of space-time itself, not a bending into something external. Also, in the rubber membrane analogy, we're using gravity itself to make the ball sink into the sheet. That's circular reasoning when we're attempting to explain gravity. So while the analogy aids visualization, don't interpret it too literally. What does space-time curvature actually mean? The rules of geometry are different. In flat space, the shortest distance between 2 points is a straight line. But in curved space, straight lines don't exist in the conventional sense. Instead, there are geodesics, the paths representing the shortest distance between 2 points in that curved space. On Earth's surface, which is curved, the shortest path between two cities isn't a straight line through the air. If you had to remain on the surface, it's a curve following what's called a Great Circle route. Flights from New York to Beijing travel over the Arctic. It appears like a peculiar curved path on a flat map, but on a globe, it's actually the shortest route. In curved space-time, objects follow geodesics. A planet orbiting the Sun isn't being pulled by a force. It's following a geodesic through the curved spacetime created by solar mass. From the planet's perspective, it's moving in a straight line. But because spacetime is curved, that straight line from our perspective appears as an orbit. The planet is constantly falling toward the sun, but also moving sideways rapidly enough that it keeps missing, a perpetual state of freefall. This explains why astronauts orbiting Earth experience weightlessness. They're not beyond Earth's gravity. The gravitational field at the International Space Station's altitude, which orbits roughly 400 kilometers or approximately 250 miles above Earth, remains around 90% as strong as at ground level. The astronauts feel weightless not because gravity is absent, but because they're in freefall. They're following a geodesic through curved spacetime. Earth curves spacetime, and the station follows that curvature, constantly falling toward Earth but moving sideways fast enough to continually miss it. The astronauts inside are falling at identical rates as the station. So relative to the station, they float. You experience this same phenomenon when you jump for that brief moment. You're airborne, you're in freefall, you're weightless. You don't feel your weight pressing down on your feet. Of course, the moment is so brief you don't really register it. But if you could somehow extend that moment, remove the ground so you kept falling, you'd feel exactly what astronauts experience in orbit. True weightlessness. The equivalence principle. Picture yourself in an elevator when someone severs the cable. Terrible scenario, but stay with me. As the elevator plummets, you'd float inside it. You wouldn't feel your weight. You'd be in freefall along with the elevator. Alternatively, imagine you're out in deep space, distant from any planet or star. You and the elevator are drifting. You'd also float inside because there's nothing to push against. Einstein's insight. These two situations are equivalent. Freefall in a gravitational field and floating in deep space with no gravity are the same experience. You cannot distinguish the difference from inside the elevator. This is the equivalence principle, one of general relativity's foundational concepts. Similarly, standing in an elevator on Earth, you feel the floor pushing upward on your feet. That's what weight is. The floor resisting your tendency to follow a geodesic through curved spacetime. In a rocket in deep space far from any planets or stars, if the rocket accelerates at 9.8 meters per second squared, roughly 32 feet per second squared, matching the acceleration you experience from Earth's gravity, you'd feel the floor pushing up on your feet in exactly the same way. From inside the rocket, no experiment could determine whether you're standing on Earth or accelerating in deep space. These two situations are equivalent. The equivalence principle leads to strange predictions. One is gravitational time dilation. Time passes at different rates depending on where you are within a gravitational field. The stronger the gravitational field, the slower time passes. If you're standing on a massive planet's surface where spacetime is highly curved, time passes more slowly for you than for someone in orbit where spacetime is less curved. Not a perceptual thing, not that time feels slower. Time actually passes at different rates. If you had two synchronized clocks and placed one on the surface and one in orbit, when you brought them back together, they'd display different times. The one on the surface would show less time had elapsed. This has been measured experimentally many times. In 1971, scientists placed extremely accurate atomic clocks on commercial airplanes and flew them around the world. When they landed, those clocks were ahead of identical clocks that remained on the ground by exactly the amount predicted by general relativity. The difference was tiny, measured in nanoseconds, but it was real and measurable. GPS satellites orbiting Earth must account for time dilation, or their position calculations would be off by kilometers within hours. The atomic clocks on GPS satellites run slightly faster than clocks on Earth's surface, because they're higher up where spacetime is less curved. The GPS system corrects for this automatically. Every time you navigate with your phone, you're relying on Einstein's predictions being accurate. Gravitational lensing and beyond general relativity also predicts gravitational lensing. Light follows geodesics through curved spacetime just like everything else. So if light passes near a massive object, its path will curve. A massive object can act like a lens, bending light that passes near it. This was first observed in 1919 during a solar eclipse. Astronomers photographed stars near the sun during the eclipse when solar glare didn't overwhelm the starlight. They found that stars appeared slightly displaced from their known positions. Solar gravity was bending the starlight passing near it, making the stars appear in slightly different positions. The amount of displacement matched Einstein's predictions precisely. This observation made Einstein world famous overnight. Today, gravitational lensing is a standard tool in astronomy. When light from a distant galaxy passes near a massive object like a galaxy cluster positioned between us and that distant galaxy, the light gets bent. Sometimes the light takes multiple paths around the massive object, and we see multiple images of the same distant galaxy. Or the galaxy gets stretched into arcs or rings. By studying these lensed images, astronomers can map the distribution of mass in the lensing object, including dark matter, which we can't see directly, but which still curves space-time. Black holes, the most extreme curvature. Black holes are the most extreme example of curved space-time. A black hole is a region where space-time is so severely curved that nothing, not even light, can escape. The boundary of no return is called the event horizon. Once you cross it, all possible paths through space-time lead inward toward the center. There's no way out. Not because something is pulling you in, but because space-time itself is curved so extremely that all geodesics point inward. Black holes form when massive stars collapse at the end of their lives. A star is a balance between gravity trying to compress it and pressure from nuclear fusion pushing outward. As long as the star is fusing hydrogen, helium, or heavier elements in its core, the pressure keeps the star from collapsing. Eventually a massive star runs out of fuel. Fusion stops. The outward pressure disappears. Gravity wins. The star collapses. If the star is massive enough, more than roughly 20 times the Sun's mass, the collapse doesn't stop. The entire star compresses into an infinitely small point called a singularity. Around that singularity is the event horizon. The size of the event horizon depends on the mass. For a black hole with the Sun's mass, the event horizon would be around 3 kilometers, or approximately 2 miles in radius. That's called the Schwarzschild radius, after Karl Schwarzschild, who calculated it in 1916, just months after Einstein published General Relativity. For a black hole with 10 solar masses, the radius would be roughly 30 kilometers or 19 miles. For a supermassive black hole with a billion solar masses like those at galaxy centers, the radius would be nearly 3 billion kilometers or 1.9 billion miles, larger than Saturn's orbit. Something that bends people's minds. From the perspective of someone falling into a black hole, they cross the event horizon in finite time. They'd fall through in seconds or minutes or hours, depending on the black hole's mass. But from the perspective of someone watching from outside, the falling person never quite reaches the event horizon. As the person approaches the horizon, time dilation becomes increasingly extreme. Time passes slower and slower for the falling person relative to the outside observer. The light from the falling person becomes increasingly redshifted, shifting from visible light to infrared to radio waves, becoming dimmer and dimmer. Eventually the person appears to freeze just outside the event horizon, fading from view. But this is just a perspective effect. The person experiences themselves falling through normally. Inside the event horizon, space-time is so warped that the future points toward the center. Just as surely as your future in normal space-time points forward in time, your future inside a black hole points toward the singularity. You can no more avoid hitting the singularity than you can avoid moving forward in time. The singularity isn't a place in space you can avoid by moving sideways. It's a moment in your future that you will inevitably reach. At the singularity, space-time curvature becomes infinite. Matter is compressed to infinite density. Our current theories break down. General relativity predicts the singularity but can't describe what happens there because the mathematics gives infinities, which usually means the theory has reached its limits. Most physicists think that quantum effects, which general relativity doesn't include, become important at some point before you reach the true singularity. But we don't have a complete theory of quantum gravity yet, so we can't say for certain what happens at a black hole's very center. The singularity raises profound questions about spacetime's nature itself. Is infinite curvature physically real, or does it signal that our description fails? Some physicists think spacetime itself might dissolve at the Planck scale, approximately 10 to the negative 35 meters, replaced by something more fundamental, perhaps a quantum foam where space and time lose their classical meaning. The singularity might not be a point of infinite density, but rather a region where our concepts of space and time simply stop applying. There's also the cosmic censorship conjecture proposed by Roger Penrose. It states that all singularities are hidden inside event horizons, invisible to outside observers. Nature seems to enforce this rule. We don't see naked singularities, singularities without event horizons. Why? If naked singularities existed, light from them could reach us, and we'd observe regions where physical laws break down, where predictability fails. The universe would have visible flaws in its causal structure. Cosmic censorship protects us from this, though we don't fully understand why nature enforces it. Common misconceptions about black holes. There's considerable misconception about black holes. People think they're like cosmic vacuum cleaners, sucking in everything around them. Not true. A black hole only pulls on things gravitationally just like any other object with mass. If the Sun suddenly became a black hole with the same mass, which it won't because it's not massive enough, Earth's orbit wouldn't change. We'd still orbit at the same distance. We'd freeze because the Sun wouldn't be radiating light and heat anymore, but we wouldn't get sucked in. You only encounter trouble with a black hole if you get very close. Closer than you could approach a normal star because the star's physical surface would be in the way. With a black hole, the physical matter has collapsed inside the event horizon, so you can get much closer to the centre of mass. That's when tidal forces become extreme. Tidal forces are differences in gravitational pull across an object. Earth's tides are caused by the Moon pulling slightly harder on the side of Earth facing it than on the side facing away. With normal objects like Earth or the Moon, tidal forces are gentle, but near a black hole, they become savage. If you fell feet first toward a black hole, your feet would be closer to the black hole than your head. The pull on your feet would be stronger than the pull on your head. The difference would stretch you. As you got closer, the stretching would become increasingly extreme. Eventually, you'd be pulled apart, stretched like spaghetti. Physicists have a term for this, spaghettification, a real term used in technical papers. For a small black hole, spaghettification would occur before you even reached the event horizon. For a supermassive black hole, the event horizon is so far from the centre that tidal forces at the horizon are relatively gentle. You could cross the event horizon without immediately being torn apart. You'd only get spaghettified much later as you fell closer to the singularity. Hawking radiation. Black holes aren't completely black. In 1974, Stephen Hawking predicted that black holes emit radiation due to quantum effects near the event horizon, now called Hawking radiation. The basic idea is that empty space isn't truly empty. Quantum mechanics tells us that particle-antiparticle pairs are constantly popping into existence and then annihilating each other almost immediately. This normally doesn't lead to anything observable. But near a black hole's event horizon, one particle might fall into the black hole while the other escapes. From outside, it looks like the black hole is emitting radiation. This radiation carries energy away from the black hole, so the black hole gradually loses mass and shrinks over time. Black hole evaporation. The effect is incredibly slow for large black holes. A black hole with the Sun's mass would take approximately 10 to the 67 years to evaporate. That's 10 with 67 zeros after it. For comparison, the universe is only roughly 13.8 billion years old. That's around 10 to the 10 years. So a solar mass black hole would take vastly longer than the current age of the universe to evaporate. For supermassive black holes, the evaporation time is even longer, far beyond any meaningful timescale. But for tiny black holes, if they exist, evaporation could be fast. A black hole with the mass of a mountain would evaporate in approximately 1 billion years. A black hole with the mass of a ship would explode in a fraction of a second, releasing energy equivalent to multiple nuclear bombs. Fortunately, or unfortunately, depending on your perspective, we've never observed any primordial black holes of such small size, and we don't know if they exist. Gravitational waves, ripples in spacetime. Gravitational waves are one of the most spectacular conformations of general relativity. According to Einstein's theory, accelerating masses produce ripples in spacetime itself. These ripples travel outward at the speed of light, carrying energy away from their source. Imagine throwing a stone into a pond. Ripples spread out across the water's surface. Gravitational waves are similar, except they're ripples in the fabric of spacetime itself. As a gravitational wave passes through a region of space, it alternately stretches and squeezes that space in perpendicular directions. Einstein predicted gravitational waves in 1916, but thought they'd be far too weak to ever detect. For decades, they remained purely theoretical. Then, in the 1970s, astronomers Russell Hulse and Joseph Taylor discovered a binary pulsar, two neutron stars orbiting each other. They observed that the orbit was gradually decaying. The two stars were slowly spiraling inward. The rate of decay matched exactly what you'd expect if the system was losing energy to gravitational waves, indirect evidence that gravitational waves exist. Hulse and Taylor won the Nobel Prize with this discovery in 1993. But detecting gravitational waves directly required building incredibly sensitive instruments. In the United States, scientists built the Laser Interferometer Gravitational Wave Observatory, LIGO. LIGO consists of two facilities, one in Louisiana and one in Washington state, separated by 3,000 kilometers or 1,900 miles. Each facility has two arms 4 kilometers or 2.5 miles long, arranged in an L shape. Laser beams bounce back and forth along these arms. If a gravitational wave passes through, it stretches space in one direction and squeezes it in the perpendicular direction. The change in distance is incredibly small. When LIGO made its first detection, the change was roughly 1/10,000th the diameter of a proton. Like measuring the distance to the nearest star to within the width of a human hair, the precision required is almost incomprehensible. On September 14, 2015, both LIGO detectors picked up a signal. A gravitational wave had swept through Earth. By analysing the signal, scientists determined it came from two black holes, 29 and 36 times the Sun's mass, spiralling into each other 1.3 billion light-years away. As the black holes orbited each other, they emitted gravitational waves, losing energy and spiralling inward faster and faster. In the final fraction of a second, they merged, creating a single black hole 62 times the Sun's mass. Wait a minute. 29 plus 36 equals 65, not 62. What happened to those three solar masses? They were converted entirely into gravitational wave energy, according to Einstein's famous equation E equals mc squared. In a fraction of a second, this merger released more energy in gravitational waves than all the stars in the observable universe were emitting in light at that moment. The power output during that brief moment was roughly 50 times the power output of all the stars in the universe combined. Hard to wrap your mind around that. Since that first detection, LIGO and its European counterpart Virgo have detected dozens of gravitational wave events. Most are black hole mergers, but some are neutron star mergers. In 2017, LIGO and Virgo detected gravitational waves from two neutron stars colliding. This event was also observed with traditional telescopes across the electromagnetic spectrum, from gamma rays to radio waves. The first time an astronomical event was observed with both gravitational waves and light. This ushered in a new era of multi-messenger astronomy, where we study cosmic events using different kinds of signals. What gravitational waves tell us? What makes gravitational wave astronomy revolutionary isn't just detecting these events, it's what we learn from them. When neutron stars merge, the gravitational wave signal encodes information about their internal structure. Neutron stars are laboratories for extreme physics, with matter compressed to densities where atomic nuclei merge into exotic states. Different theories about how matter behaves under these conditions, different equations of state, predict slightly different gravitational wave signatures during a merger. By analysing the waves, we're essentially probing the interior structure of neutron stars, conducting experiments on matter at nuclear densities that we could never achieve on Earth. These observations also test fundamental physics. The speed of gravitational waves equals the speed of light to extraordinary precision. This wasn't guaranteed by theory. Some alternative theories of gravity predict different speeds. The LIGO-Virgo observations constrain or rule out entire classes of modified gravity theories. Every detection is simultaneously a discovery and a test, building confidence in general relativity while searching for any deviation that might point toward new physics. Gravitational waves also offer a unique way to measure cosmic distances. The amplitude of the wave tells us how far away the source is, while the frequency evolution tells us the masses of the merging objects. If we can also identify the host galaxy with traditional telescopes, we can measure both the distance and the galaxy's recession velocity. This gives us an independent measurement of the universe's expansion rate, potentially resolving current tensions between different measurement methods that give slightly different results. Gravitational wave cosmology might answer one of the most pressing questions in modern astronomy. Is the universe expanding faster or slower than our standard model predicts? Gravitational waves give us a completely new way to observe the universe. Light can be blocked by dust or gas, but gravitational waves pass through matter almost unimpeded. They carry information about events we could never see with traditional telescopes, like the insides of supernovas or the very early universe moments after the Big Bang. The coming decades, even more sensitive gravitational wave detectors will be built. The Laser Interferometer Space Antenna, LISA, will consist of 3 spacecraft arranged in a triangle with sides 5 million kilometers or 3 million miles long. It will detect lower frequency gravitational waves from sources like supermassive black holes merging at galaxy centers, events LIGO can't detect because it's designed for higher frequencies. The dark universe. Dark matter and dark energy have puzzled scientists for decades. When astronomers study galaxies, they measure how fast stars orbit the galactic center. Based on visible matter, stars on the outer edges should move much slower than they do. The only explanation is additional mass we can't see, providing extra gravitational pull. We call this dark matter. It doesn't emit light or any electromagnetic radiation. That's why it's dark. But it has mass. So it curves spacetime and affects visible matter through gravity. Roughly 85% of the matter in the universe is dark matter. Only 15% is ordinary matter that makes up stars, planets, and people. What is dark matter? We don't know. It's not just dark clouds of normal matter like planets or dust, because such objects would absorb and block light from objects behind them. Dark matter doesn't do that. It's completely transparent. Leading theories suggest it's made of undiscovered subatomic particles that don't interact with light or normal matter except through gravity. Scientists are building detectors deep underground to try to catch dark matter particles colliding with normal atoms. So far, they haven't detected anything conclusive. The search continues. Dark energy is even more mysterious. In 1998, astronomers studying distant supernovas made a shocking discovery. The universe's expansion is accelerating, completely unexpected. After the Big Bang, the universe started expanding. Everyone assumed that gravity would gradually slow that expansion over time. The universe might eventually stop expanding and collapse back in a big crunch, or it might expand forever but at a decreasing rate. But acceleration? That suggested something was pushing the universe apart, counteracting gravity. This mysterious something is called dark energy. It appears to be a property of space itself. As the universe expands, creating more space, there's more dark energy. This drives faster expansion, which creates even more space and even more dark energy, a runaway process. Dark energy makes up roughly 68% of the total energy content of the universe. Dark matter is around 27%. Ordinary matter is approximately 5%. We live in a universe where 95% of it is stuff we don't understand. That should be humbling. The existence of dark energy has profound implications for the universe's fate. Because the expansion is accelerating, distant galaxies are moving away from us faster and faster. Eventually, they'll be moving away so fast that their light can no longer reach us. In the far future, trillions of years from now, the universe will be a much lonelier place. Most galaxies will be beyond our cosmic horizon. Only the galaxies in our local group, held together by gravity into a single structure, will remain visible. The rest of the universe will have expanded away beyond reach. Civilizations arising in that distant future would look out and see only their own galaxy and a handful of neighbors. They'd have no way to know the universe had ever been larger or fuller. Everything we've learned about cosmology, the Big Bang, the expansion of the universe, would be inaccessible to them. They'd be observationally cut off from understanding the history and structure of the cosmos. We're fortunate to exist at a time when we can still observe and study the broader universe. Cosmology and the Big Bang cosmology is the study of the universe as a whole. General relativity describes not just gravity, but the structure and evolution of the entire universe. In 1922, Alexander Friedmann used Einstein's equations to show that the universe must be either expanding or contracting. It can't be static. Einstein initially resisted this, believing the universe was eternal and unchanging. Then in 1929, Edwin Hubble observed that distant galaxies are moving away from us. The farther away a galaxy is, the faster it's receding. This proved the universe is expanding. Space itself is stretching, carrying galaxies apart. If the universe is expanding now, it must have been smaller in the past. Wind the clock backward far enough, and everything was compressed into an incredibly hot, dense state. The Big Bang. Not an explosion in space, but the expansion of space itself. The evidence is overwhelming. First, galaxies are moving apart. Second, the universe is filled with microwave radiation called the cosmic microwave background, the afterglow of the Big Bang from when the universe was only around 380,000 years old. Third, the abundances of light elements match predictions. In the first few minutes after the Big Bang, nuclear fusion created hydrogen, helium, and traces of lithium. The ratios we measure today match the predictions precisely. The Big Bang theory says the universe had a beginning roughly 13.8 billion years ago. Before that, there was no before in any meaningful sense, because time itself began with the Big Bang. Asking what came before the Big Bang is like asking what's north of the North Pole, a meaningless question. Time is part of the universe, part of space-time. When space-time began, time began. There was no earlier time. The first fractions of a second after the Big Bang are where things get speculative. At extremely high temperatures and densities, we need a theory of quantum gravity to describe what happens. We don't have one yet. String theory, loop quantum gravity, and other approaches are being developed, but none are complete or confirmed. So we can't say with certainty what happened in the very first instant. But we can say with confidence what happened from around 1 second onward, because our theories work well in that regime and match observations perfectly. The shape and fate of the universe. One question people often ask is whether the universe is infinite or finite. The answer is we don't know. The observable universe is finite. It's the region of space from which light has had time to reach us since the Big Bang, approximately 93 billion light-years across. Beyond that is space we can't see, because light from those regions hasn't reached us yet. But that doesn't mean the universe ends there. Space could extend far beyond what we can observe, perhaps infinitely. Current observations suggest the universe is spatially flat on the larger scales, which is consistent with it being infinite. But it could also be very large but finite, curved back on itself like the surface of a sphere is finite but has no edge. We don't have enough information to know for sure. Additional predictions of general relativity. Other predictions of general relativity deserve mention. One is frame dragging. A massive rotating object drags space-time around with it as it spins. The effect is incredibly small for objects like Earth, but it has been measured. In 2004, NASA launched Gravity Probe B, a satellite carrying 4 ultra-precise gyroscopes. These gyroscopes were so perfectly spherical that if you scaled them up to Earth's size, the tallest mountains would be only around 2 meters or 6 feet high. The satellite orbited Earth for over a year, measuring tiny changes in the gyroscope's orientations caused by frame dragging. The results confirmed Einstein's predictions. Earth's rotation drags, space-time around with it, and the gyroscopes detected that drag. Frame dragging is much more significant near rapidly rotating black holes. A black hole can have 3 properties: mass, electric charge, and angular momentum, which means it's spinning. Most black holes probably have little to no charge because charge tends to attract opposite charges and neutralize. But angular momentum is different. If a star is rotating when it collapses, and all stars rotate at least a little, the resulting black hole will be spinning. A spinning black hole drags space-time around it in a vortex. This creates an ergosphere, a region outside the event horizon, where space-time is being dragged around so forcefully that nothing can remain stationary. You'd have to move along with the rotation. In principle, you could extract energy from a rotating black hole using a process called the Penrose process. You drop an object into the ergosphere. The object splits into 2 pieces. One piece falls into the black hole, carrying negative energy from the black hole's perspective. The other piece escapes with more energy than the original object had. The black hole loses angular momentum and slows down. You've extracted rotational energy from the black hole. This might sound like science fiction, but it's a legitimate consequence of general relativity. Whether any civilization could actually do this in practice is another question. Another fascinating prediction involves closed time-like curves, which are paths through space-time that loop back on themselves, allowing travel into the past. In certain solutions to Einstein's equations, like the Gödel metric and rotating wormholes, these paths exist. You could in principle travel along such a path and arrive at an earlier time. This raises all the problems with time travel, like paradoxes. If you went back in time and prevented your own birth, would you still exist to go back? General relativity doesn't forbid closed time-like curves, but most physicists think they're impossible for other reasons. Perhaps quantum mechanics prevents them. Perhaps the conditions needed to create them are physically unrealizable. Or perhaps they exist, but information or objects traveling through them would be destroyed by quantum effects. We don't know. It's an open question. Testing general relativity. General relativity has been tested in many ways over the past century, and it's passed every test with flying colours. But we know it's not the final theory. It's incompatible with quantum mechanics, our other fundamental theory. Quantum mechanics describes the microscopic world of atoms and particles. General relativity describes the macroscopic world of stars and galaxies. Both theories work brilliantly in their respective domains. But when you try to apply both to the same situation, like the interior of a black hole or the first instant of the Big Bang, they give contradictory answers. We need a unified theory of quantum gravity. String theory and loop quantum gravity are leading candidates, but neither is confirmed. Until we have a complete quantum theory of gravity, there will be aspects of the universe we can't fully understand. Despite this, general relativity remains one of the most successful theories in science. It has revolutionized our understanding of the cosmos. It predicted black holes, gravitational waves, the Big Bang, and much more, all of which have been confirmed. It's the foundation of modern cosmology, and it all comes from a simple but profound idea. Gravity isn't a force, it's the curvature of spacetime, your personal experience of curved spacetime. Consider your current experience. You're sitting or standing somewhere right now. You feel weight. If you're sitting, you feel the chair pushing up on you. If you're standing, you feel the floor beneath your feet. In Newtonian terms, this would be gravity pulling you down. But general relativity reveals something more subtle. The chair or floor exerts electromagnetic forces that resist your body's natural tendency to move along a particular path through space-time. A geodesic that would take you toward Earth's center. What you interpret as weight is actually the sensation of this resistance, not a downward pull. If the floor suddenly vanished and you started falling, you'd feel weightless. Not because gravity stopped, but because you're now free to follow your geodesic. Freefall, your natural state of motion in space-time. Astronauts in orbit are weightless because they're in freefall, nothing pushing on them. They're experiencing their natural motion through space-time. From the perspective of space-time geometry, freefall is the natural state. Weight is the abnormal state caused by something pushing on you. We usually think of it the opposite way. We think sitting still is natural and falling requires an explanation. But from the viewpoint of general relativity, falling is natural and sitting still requires an explanation. That explanation is the electromagnetic forces from the floor or chair preventing you from following your geodesic. This might seem like word games, but it has real consequences. It changes how we think about motion and forces. In Newtonian physics, you need a force to change an object's motion. An object at rest stays at rest unless a force acts on it. An object in motion stays in motion in a straight line unless a force acts on it. Gravity is the force that makes things fall. But in general relativity, gravity isn't a force. An object in free fall is following the straightest possible path through curved space-time. No force is needed. Electromagnetic forces, the resistance of matter, change your motion by preventing you from falling. This perspective helps explain why all objects fall at the same rate in a vacuum regardless of their mass. Galileo supposedly dropped 2 balls of different weights from the Leaning Tower of Pisa to demonstrate this. Whether he actually did that experiment is disputed, but the principle is true. In the absence of air resistance, a feather and a hammer fall at the same rate. The Apollo 15 astronauts demonstrated this on the Moon where there's no air. They dropped a feather and a hammer simultaneously, and both hit the ground at the same time. In Newtonian physics, this is a curious coincidence. The gravitational force on an object is proportional to its mass, but the acceleration produced by a force is inversely proportional to mass. The two effects exactly cancel, giving the same acceleration regardless of mass. Why? Newton couldn't explain it. It's just how nature worked. But in general relativity, it makes perfect sense. Objects aren't being pulled by a force proportional to their mass. They're following geodesics through spacetime. The curvature doesn't care about an object's mass. All objects follow the same geodesics, so they all fall at the same rate. Natural and inevitable, not a curious coincidence. Why you can't feel gravity in freefall? Why can't you feel gravity during freefall? In a small enough region of spacetime, every part of your body follows essentially the same path through curved spacetime. There are no differential forces stretching or compressing you. Gravity becomes locally undetectable, the equivalence principle in action. You can't distinguish between floating in deep space and freely falling in a gravitational field from within your own reference frame. However, in a large enough region, or for a long enough time, tidal forces become noticeable. These are caused by the curvature of spacetime varying from place to place. Your feet might be following a geodesic that converges slightly with the geodesic your head is following. Over a large enough distance, this convergence becomes significant. That's a tidal force. For objects in orbit around Earth, tidal forces are tiny. The International Space Station is only around 400 kilometers, or 250 miles from Earth's center, which is very close compared to Earth's radius of 6,400 kilometers, or 4,000 miles. The curvature doesn't vary much over that short distance. But for an object falling into a black hole, tidal forces become enormous, because spacetime curvature changes rapidly with distance, the experimental confirmation of Einstein's theory. Experimental tests have confirmed general relativity repeatedly. The first test was the deflection of starlight during the solar eclipse of 1919. According to Newton, light shouldn't be affected by gravity because light has no mass. But according to Einstein, light follows geodesics through curved spacetime. The sun curves spacetime, so light passing near it should have its path bent. Arthur Eddington led expeditions to observe the eclipse from two locations, Sobral in Brazil and Principe, an island off West Africa. The idea was to photograph stars near the sun's disk during the eclipse and compare their positions to their known positions when the sun wasn't nearby. If Einstein was right, stars should appear displaced because their light had been bent by solar gravity. The results showed displacement of approximately 1.8 arc-seconds for light grazing the solar surface, less than 1/12,000th of a degree, but it was measurable and matched Einstein's predictions. This made front-page news worldwide. Einstein became a celebrity overnight. The New York Times headline read, "Lights all askew in the heavens, men of science more or less agog." Since then, gravitational lensing has been observed countless times with far greater precision. Modern telescopes routinely see lensed images of distant galaxies bent into multiple images, or arcs by galaxy clusters in the foreground. We use gravitational lensing as a tool to map the distribution of mass, including dark matter in those clusters. Another key test was the perihelion precession of Mercury mentioned earlier. When Einstein completed general relativity in 1915, one of the first things he did was calculate Mercury's orbit. General relativity predicts that spacetime curvature near the Sun causes extra precession. When Einstein calculated the amount, he got exactly 43 arc-seconds per century. The decades-old mystery was solved in an instant. Einstein later said this was one of the happiest moments of his life. Gravitational redshift provides another crucial test. Light climbing out of a gravitational well loses energy. For light, energy is related to frequency. Lower energy means lower frequency and longer wavelength. For visible light, this shifts the colour toward the red end of the spectrum. First measured in 1960 using the Mersbauer effect, a technique that allows extremely precise measurements of frequency. Scientists put a radioactive source at the top of a tower and a detector at the bottom. The gamma rays emitted by the source were slightly redshifted by the time they reached the detector, exactly as general relativity predicted. Light from the Sun shows a small but measurable redshift compared to laboratory sources. From white dwarf stars, the redshift reaches approximately 50 parts per million. From neutron stars, light is redshifted by around 30%. Near a black hole's event horizon, photons climbing out lose so much energy that the redshift becomes enormous. Light barely escaping the horizon shifts to infinitely low frequencies. This redshift also appears cosmologically. As the universe expands, light travelling through space gets stretched, its wavelength increasing. By measuring how much distant galaxies light has redshifted, we determine their distance and how long ago that light was emitted. Time dilation has also been measured using extremely accurate atomic clocks. In 2010, scientists at the National Institute of Standards and Technology showed they could detect time dilation over a height difference of just 33 centimeters, or roughly 1 foot. They placed 2 atomic clocks, one 33 centimeters higher than the other. The higher clock ticked slightly faster because it was in a slightly weaker gravitational field. The difference was only around 90 trillionths of a second per day, but it was measurable. Stunning precision that shows general relativity holds even for tiny differences in gravitational potential. The orbit decay of binary pulsars is another crucial test. A pulsar is a rapidly rotating neutron star that emits beams of radio waves from its magnetic poles. As the pulsar rotates, these beams sweep across space like a lighthouse beam. If one of these beams points toward Earth, we see regular pulses of radio waves. Some pulsars are in binary systems orbiting another neutron star or a white dwarf. The Hulse-Taylor binary pulsar consists of 2 neutron stars orbiting each other every 7.75 hours. General relativity predicts that this system should emit gravitational waves. As it does, it loses energy. The orbit should shrink and the orbital period should decrease. Hulse and Taylor monitored the system for years and found that the orbital period was decreasing by exactly the amount predicted if the system was radiating gravitational waves. Over decades of observations, the agreement has been extraordinary. The orbit is decaying at precisely the predicted rate. This was the first indirect evidence that gravitational waves exist, decades before LIGO detected them directly. The direct detection of gravitational waves by LIGO is perhaps the most spectacular confirmation of general relativity. Not only did LIGO detect waves, but the waveform, the shape of the signal, matched predictions from computer simulations of black hole mergers. By analyzing the signal, scientists could determine the masses of the merging black holes, their spins, how far away the merger happened, and many other details. The match between observation and theory is remarkable. General relativity predicts not just that gravitational waves exist, but their exact properties and how they propagate through spacetime. The LIGO detections confirm all of this. General relativity has also been tested in strong field regimes near black holes. The Event Horizon Telescope, a global network of radio telescopes working together, took the first image of a black hole shadow in 2019. The black hole is at the center of the galaxy M87, approximately 55 million light-years away. The image shows a dark central region, the black hole's shadow, surrounded by a bright ring of emission from hot gas orbiting the black hole. The size and shape of the shadow match predictions from general relativity. If gravity worked differently, the shadow would look different. In 2022, the Event Horizon Telescope imaged the black hole at the center of our own galaxy, Sagittarius A. Again, the image matched predictions. These observations are testing general relativity in some of the most extreme conditions in the universe, near supermassive black holes where space-time is severely warped, and the theory still holds, the quest for quantum gravity. You might wonder, if general relativity has passed every test, why do we think it might be wrong or incomplete? The reason is that it doesn't account for quantum mechanics. Quantum mechanics is the theory of the microscopic world. It describes how particles like electrons, photons, and quarks behave. Quantum mechanics is probabilistic. It deals with waves of probability. Particles don't have definite positions or velocities until you measure them. Before measurement, they exist in a superposition, a combination of many possible states. Measuring the particle collapses this superposition, and you get one specific outcome. This is completely alien to general relativity, which is deterministic. In general relativity, if you know the curvature of space-time and the positions and velocities of objects at one time, you can calculate their past and future trajectories with certainty. There's no probability, no uncertainty, no superpositions. The theories operate on different principles and don't fit together. For most situations, that's not a problem. Quantum mechanics handles the small stuff. General relativity handles the big stuff. They rarely need to work together, but in certain extreme situations, both are important. Inside a black hole, for instance, spacetime curvature becomes infinite at the singularity. But at such small scales and high densities, quantum effects must be significant. We need a theory that combines quantum mechanics and general relativity to describe what happens. Similarly, at the very beginning of the Big Bang, the entire universe was smaller than an atom. Quantum effects were crucial, but so was the curvature of space-time. Again, we need a unified theory. String theory is one attempt to unify quantum mechanics and gravity. In string theory, particles aren't point-like, they're tiny vibrating strings. Different vibration patterns correspond to different particles, electrons, photons, quarks, all are different vibrations of the same fundamental strings. Gravity emerges naturally in string theory. The graviton, the hypothetical particle that carries the gravitational force, is one of the vibration patterns. String theory requires extra dimensions of space beyond the 3 we experience. Current versions suggest 10 or 11 total dimensions. The extra dimensions are supposedly curled up so small we don't notice them, but this is speculative. String theory makes few testable predictions, and so far none have been confirmed or falsified. It's mathematically elegant, but it's not clear if it describes the real world. Loop quantum gravity takes a different approach. It tries to quantize spacetime itself, treating it not as a smooth continuum but as a network of tiny loops. Space and time would be discrete at the smallest scales, coming in indivisible chunks. This would prevent the infinities that plague our current theories, but loop quantum gravity also struggles to make testable predictions. There are other approaches too, theories involving higher dimensions, theories where gravity is an emergent phenomenon arising from something more fundamental, even theories questioning whether spacetime is fundamental at all. The truth is we don't know. Quantum gravity is one of the biggest unsolved problems in physics. Until we solve it, our understanding of the universe will be incomplete. We won't fully understand the Big Bang, the insides of black holes, or the ultimate fate of information that falls into a black hole, some of the deepest mysteries in science. What general relativity means for you. What does general relativity mean for you personally? For most people, most of the time the effects are too small to notice. Navigation relies on general relativity, but you don't think about that when you use your phone. The time dilation you experience standing up versus sitting down is roughly 10 trillionths of a second per day. You'll never notice. So why does it matter? It matters because understanding general relativity changes how you see reality. You live in a universe where space and time are unified into spacetime. Spacetime is flexible, curved by mass and energy. You're not held to Earth by an invisible force pulling you down. You're following the natural contours of curved spacetime. Every object in the universe, from a grain of sand to a galaxy cluster, curves spacetime around it. These curvatures interact in complex ways, creating the rich tapestry of motion we observe. Planets orbiting stars, stars orbiting galactic centers, galaxies clustering together, all of it is objects following geodesics through a dynamically curving 4-dimensional spacetime. When you look up at the night sky, you're seeing objects separated by vast distances, but you're also seeing the past. Light takes time to travel. The light from the sun is 8 minutes old when it reaches you. Light from the nearest star is over 4 years old. Light from distant galaxies is billions of years old. You're literally looking back in time. The universe has a history written in light, and that light has been travelling through curved space-time to reach your eyes. You're also part of this cosmic story. The atoms in your body were forged in stars billions of years ago. Those stars exploded as supernovas, scattering their atoms into space. Over eons, those atoms drifted, eventually coming together in a cloud of gas that collapsed under its own gravity to form our solar system. Earth formed from that material, and eventually, after billions of years of evolution, those atoms arranged themselves into you. You're made of stardust. Not a metaphor. Literally true. The carbon in your cells, the iron in your blood, the calcium in your bones, all were created in stellar furnaces and supernova explosions and have been travelling through the cosmos for billions of years before ending up in you. General relativity tells us that spacetime itself is dynamic, not a static stage on which events unfold, but an active participant. It curves in response to mass and energy. Those curves affect how matter moves, and that moving matter curves spacetime in turn. A feedback loop. This dynamic interplay between matter and spacetime gives rise to all the gravitational phenomena we observe, from falling apples to black hole mergers to the expansion of the universe itself. A philosophical perspective. There's a deep philosophical implication too. In Newton's view, space and time were absolute. They existed independently of the matter and events within them. They provided a fixed framework for the universe. But Einstein showed this isn't true. Spacetime is relational. It's defined by the events and objects within it. Take away all the matter and energy, and it's not clear that space-time would even exist in a meaningful sense. The universe is not a container with stuff inside it. The universe is the stuff, and the relationships between the stuff. Space-time is those relationships. This might sound abstract, but it has consequences. The universe is self-contained. There's no outside. The question, what's outside the universe, it doesn't make sense because outside implies a spatial relationship, and space is part of the universe. Similarly, what happened before the Big Bang doesn't make sense if time began with the Big Bang. These are questions that feel like they should have answers, but they're based on concepts that don't apply at the most fundamental level. Some people find this unsettling. The universe doesn't have an external explanation. It is the explanation. Others find it liberating. The universe is comprehensible on its own terms. We don't need to invoke anything outside it to understand how it works. The laws of physics, the properties of space-time, the constants of nature, these are the foundations, and everything builds from there. The future of gravitational physics. Where is gravitational physics headed? One exciting area is testing general relativity in even more extreme conditions. The Event Horizon Telescope is continuing to observe black holes, looking for any deviations from predictions that might hint at new physics. Future observations will track matter spiraling into black holes in real time, watching how space-time curvature affects the trajectories and emissions of doomed gas clouds. Scientists are particularly interested in measuring the photon ring, a bright, narrow band of light that orbits just outside the event horizon, completing multiple circuits before escaping to our telescopes. The exact structure of this ring encodes information about the black hole's spin and properties in ways that will test general relativity with unprecedented precision. Gravitational wave detectors are becoming more sensitive. LIGO is being upgraded, new detectors are being built in Japan and India, and LISA, the space-based detector, is planned for the 2030s. These will observe gravitational waves from a wider range of sources, giving us more opportunities to test general relativity and explore phenomena we can't study any other way. LISA's sensitivity to low-frequency waves will reveal supermassive black hole mergers occurring when distant galaxies collide, events that happen too slowly for ground-based detectors but that release staggering amounts of energy. Each detection adds another data point, confirming Einstein's equations work even in the most violent events the universe produces. Beyond confirmation, gravitational waves offer unique scientific opportunities. They let us study neutron star interiors, regions so dense that atomic nuclei merge into exotic matter states we can't reproduce in laboratories. When two neutron stars spiral together and merge, the gravitational wave signal encodes information about how matter behaves at nuclear densities and beyond, different equations of state. The relationships between pressure, density, and temperature in ultra-dense matter produce subtly different waveforms. By analyzing these signals, we're essentially conducting experiments on matter, compressed far beyond anything achievable on Earth. Another frontier is the quest for quantum gravity. Several experiments are being designed to probe the interface between quantum mechanics and gravity. These are incredibly challenging because quantum gravitational effects are expected to be significant only at the Planck scale, approximately 10 to the negative 35 meters, 20 orders of magnitude smaller than a proton. We can't build particle accelerators that reach those energies, but there might be subtle effects we can measure indirectly. For instance, if space-time is discrete at the Planck scale, that might affect the propagation of light over cosmic distances in ways we could detect with sensitive enough instruments. Photons of different energies might travel at slightly different speeds through quantized space-time, arriving at Earth at slightly different times after journeying billions of light-years. No such effect has been detected yet, which constrains theories of quantum gravity. Some proposed theories predicted effects large enough that we should have seen them by now. Their absence rules out entire classes of quantum gravity models. There are also experiments testing whether gravity affects quantum superpositions. In quantum mechanics, objects can exist in superpositions of multiple states simultaneously until measured. But what happens when the objects are massive enough that their gravitational fields become significant? Does space-time itself become entangled with quantum states? Can you have a superposition of different space-time geometries? These questions probe the boundary between quantum mechanics and general relativity. Experiments with increasingly massive objects in quantum superpositions, perhaps molecules or even tiny mirrors, might reveal where quantum behavior breaks down and classical spacetime emerges, potentially pointing toward the correct theory of quantum gravity. Gravity as a tool. Astronomers are also using gravity as a tool in increasingly sophisticated ways. Gravitational lensing can magnify distant objects, allowing us to see galaxies and stars that would otherwise be too faint. By studying how gravity bends light, we can map the distribution of dark matter in galaxy clusters. We can even use lensing to detect exoplanets, planets orbiting other stars, when the planet's gravity focuses light from a background star toward us in a brief brightening event. More dramatically, gravitational lensing sometimes creates Einstein crosses or Einstein rings, patterns where we see multiple images of a single distant quasar arranged around a foreground galaxy. The foreground galaxy's mass curves spacetime so much that light from the background quasar takes multiple paths around it, each path arriving at Earth from a slightly different direction. By measuring the time delays between these multiple images, how long light takes to travel each path, astronomers can determine the expansion rate of the universe with impressive accuracy. Different paths through curved spacetime have different lengths, so light traveling them arrives at different times. This technique provides an independent measurement of cosmic expansion that doesn't rely on traditional distance ladder methods, helping resolve ongoing debates about whether the universe is expanding faster or slower than our models predict. There's also the tantalizing possibility of detecting primordial gravitational waves, ripples in spacetime produced in the first moments after the Big Bang. These waves would carry information about the universe when it was far younger and smaller than anything we can currently observe. Detecting them would be a monumental achievement, opening a window into the earliest moments of cosmic history. Current experiments search for these primordial waves by looking at the cosmic microwave background, the afterglow of the Big Bang. Gravitational waves passing through space in the early universe would have left a distinctive pattern in the polarization of this ancient light, a swirling pattern called B-modes that would be the smoking gun signature of inflation, the hypothesized period of exponential expansion that occurred in the first fraction of a second after the Big Bang. The stakes are enormous. Detecting primordial gravitational waves would confirm inflation occurred, tell us about the energy scale at which it happened, and potentially reveal physics operating at energies 1 trillion times higher than anything we can achieve in particle accelerators. It would be like having a telescope that sees back to when the universe was only a tiny fraction of a second old, revealing conditions closer to the Big Bang than any other observation method can access. Practical applications beyond pure science. Understanding gravity has practical technological implications. GPS is the most obvious example, but there are others. Gravitational wave detectors require developing laser systems, vibration isolation, and measurement techniques of extraordinary precision. These technologies spin off into other fields. The same laser stabilization methods now help atomic clocks, ultra-sensitive measurements of material properties, and fundamental physics experiments. The mirror coatings developed for gravitational wave detectors, which must reflect light with minimal losses, find applications in telecommunications and optical instruments. Looking further ahead, some physicists speculate about manipulating spacetime curvature for propulsion. If we could generate strong gravitational fields artificially, perhaps spacecraft could surf waves in spacetime or create localized distortions that effectively move space around the ship rather than moving the ship through space. The Alcubierre drive is the most famous such proposal. Contract space in front of your ship and expand it behind, effectively moving faster than light without actually accelerating through space. Unfortunately, such schemes require exotic matter with negative energy density, something that may not exist or may be impossible to produce in sufficient quantities. Still, the fact that general relativity's equations permit such solutions, even if nature doesn't provide the ingredients, shows how profoundly different this theory is from Newtonian gravity. More plausibly, understanding gravity deeply might help with long-term space exploration challenges. Rotating space habitats use centrifugal acceleration to simulate gravity, an application of the Equivalence Principle. Future habitats might use more sophisticated arrangements, perhaps varying rotation rates to create different effective gravity levels for different purposes. Generating artificial gravity becomes crucial for long-duration missions where bone loss and muscle atrophy in zero gravity pose serious health risks. A testament to human achievement, general relativity has fundamentally reshaped our understanding of the universe. Not just a better version of Newton's theory, a completely different way of thinking about space, time, matter, and gravity. And it's been confirmed by every experiment and observation to date, one of the great intellectual achievements of humanity. One person, Albert Einstein, sitting and thinking, working out the implications of a few simple ideas, constructed a theory that describes the cosmos from the smallest scales we can probe to the largest structures we can observe. Remarkable, but the story doesn't end here. We know general relativity is incomplete. We're still searching for a deeper understanding that unifies it with quantum mechanics. We don't understand dark matter or dark energy, which make up 95% of the universe. We don't know whether the universe is finite or infinite, whether it will expand forever or eventually contract, whether there are other universes beyond our own. These are open questions. The universe still holds mysteries, and that's exciting. There's more to discover. Future scientists will look back on our time the way we look back on Newton's era. They'll appreciate what we got right, but they'll also see our blind spots, the questions we couldn't answer, the leaps we couldn't make. Science is a process of continual refinement. Each generation builds on the work of the last, getting closer to a true understanding of reality. We're part of that journey. Key takeaways? What should you take away from all this? First, gravity isn't a force in the way you've been taught. Rather, it's the curvature of space-time. Objects follow geodesics through that curved space-time. When you feel weight, you're feeling electromagnetic forces preventing you from following your natural geodesic. In freefall, you're weightless, because you're finally free to move along that natural path. Second, space and time are not separate. They're unified into space-time, and space-time is dynamic, curving in response to mass and energy. This curvature affects how objects move, which in turn affects the curvature, a beautiful interplay that gives rise to all gravitational phenomena, from planetary orbits to galaxy formation to the expansion of the universe itself. Third, general relativity has been confirmed by countless experiments and observations. From the precession of Mercury to the detection of gravitational waves to images of black hole shadows, every test has supported Einstein's theory. The GPS in your phone corrects for relativistic time dilation. Gravitational lensing reveals dark matter distributions in galaxy clusters. Gravitational wave detections opened an entirely new window on the universe, one of the most successful scientific theories ever developed. Fourth, despite its success, general relativity is incomplete. It doesn't incorporate quantum mechanics. We need a theory of quantum gravity to fully understand the universe at its most fundamental level. Inside black holes, at the moment of the Big Bang, at the Planck scale where space-time itself might be quantized. That theory hasn't been found yet. It's one of the great challenges facing physics today, with string theory, loop quantum gravity, and other approaches competing to unify our understanding. Fifth, these ideas have practical applications beyond GPS. Gravitational lensing is a tool for astronomy, magnifying distant objects and mapping dark matter. Gravitational waves are a new way to observe the universe, revealing events invisible to traditional telescopes. Understanding gravity helps us understand everything from star formation to planetary systems to the large-scale structure of the cosmos. The precision measurement techniques developed for gravitational wave detectors spin off into other technologies. The atomic clocks that test time dilation enabled better navigation, timekeeping, and fundamental physics experiments. And finally, there's something profound about understanding that you live in a universe of curved space-time. Not just an abstract mathematical concept, the fabric of reality. Every moment of your life you're moving through space-time following geodesics, experiencing time dilation relative to other observers, interacting with the curvature created by Earth and the Sun and the galaxy, and all the mass energy in the universe. You're part of a vast cosmic dance that's been going on for 13.8 billion years and will continue for trillions more. Humbling and awe-inspiring. When you drop a ball and watch it fall, you're not seeing a force pulling it down. You're seeing it follow the natural geometry of space-time. When you look up at the moon, you're seeing an object in freefall, endlessly circling Earth, because that's the geodesic, it follows through curved space-time. The universe operates according to these principles whether you understand them or not. but understanding them gives you a deeper appreciation for the reality you inhabit. Einstein once said that the most incomprehensible thing about the universe is that it's comprehensible. We're tiny creatures on a small planet, yet we've figured out the fundamental laws governing cosmic scale phenomena. We've measured the curvature of spacetime. We've detected ripples in that spacetime from black holes colliding 1 billion light-years away. We've imaged the shadows of black holes at the centers of galaxies. We've traced the history of the universe back to fractions of a second after the Big Bang. This is extraordinary. It suggests that the universe is fundamentally knowable. The laws of physics are the same everywhere. We can figure them out through careful observation, experimentation, and reasoning. That should give you hope. We're not helpless in the face of cosmic mysteries. We can understand. We have understood, and will continue to understand more. So the next time you think about gravity, don't think of it as a mysterious force pulling things down. Think of it as the shape of space-time. Think of yourself as moving through a 4-dimensional geometry, following the contours of that geometry, experiencing its curvature. You're not standing still on a flat Earth with gravity pulling you down. You're accelerating upward through curved space-time, held in place by the electromagnetic forces from the ground. The ground is pushing you up constantly, preventing you from following your natural geodesic, which would take you toward Earth's center. That's weight. That's what you feel right now. And out there in space, planets are following their geodesics around stars. Stars are following their geodesics around galactic centers. Galaxies are following geodesics through the larger scale curvature of cosmic spacetime. Light from distant galaxies has been traveling for billions of years through expanding spacetime, carrying information about the ancient universe. Gravitational waves from cataclysmic events ripple through spacetime at the speed of light, stretching and squeezing space as they pass. Black holes sit in regions where spacetime curvature becomes so extreme that not even light can escape. All of this is described by Einstein's equations. All of it follows from the idea that gravity is geometry. It's been over a century since Einstein published General Relativity. In that time, it's been tested in countless ways. It's made predictions that seemed absurd but turned out to be true. It's survived every challenge. And it's given us a picture of the universe that's richer and stranger than anyone imagined. We live in a universe of curved spacetime where black holes lurk in the centers of galaxies, where gravitational waves ripple across cosmic distances, where time passes at different rates depending on where you are, where the history of the cosmos is written in the light reaching us from distant sources. The universe, as revealed by general relativity, beautiful, profound, and real. Bringing it all together. If you've made it this far, thank you for joining me on this journey through the nature of gravity and spacetime. Understanding these concepts doesn't change your daily life in obvious ways. You'll still experience weight the same way. You'll still see objects fall. But you'll know what's really happening beneath the surface. You'll have a deeper understanding of the reality that surrounds you every moment, and that understanding connects you to something larger. Every human who has ever looked up at the stars and wondered, every scientist who has ever pursued a question into the unknown, every person who has ever refused to accept "that's just how it is" as an answer. You're part of that tradition now. The story of gravity is really the story of human curiosity. From Galileo dropping weights to test his ideas, to Newton unifying terrestrial and celestial mechanics, to Einstein reimagining the fabric of reality itself, to thousands of scientists and engineers building instruments sensitive enough to detect changes smaller than a proton, to astronomers pointing telescopes at the sky night after night, gathering data, testing predictions, pushing the boundaries of what we know. This is what we do. We look at the universe and we ask questions. We build theories and test them. We make predictions and check if they're right. Sometimes we're wrong, and that's okay. That's how we learn. Sometimes we're right, and that's thrilling. That's how we progress. But we never stop asking. We never stop exploring. Right now, somewhere, a scientist is analyzing data from a gravitational wave detector, looking for patterns in the noise. Another is writing code to simulate what happens when black holes merge. Another is teaching a classroom of students about spacetime curvature. Another is proposing a new experiment to test quantum gravity. Another is building better clocks to measure time dilation with even greater precision. The work continues, the exploration continues, and you're part of it now, simply by understanding, simply by caring, simply by taking the time to learn how the universe actually works. There's something deeply moving about the fact that we, evolved primates on a small planet orbiting an ordinary star in an ordinary galaxy, have figured this out. We've deciphered the language of the cosmos. We've learned to read the story written in the curvature of spacetime. We've detected whispers from events a billion light-years away. We've peered into the hearts of black holes. We've traced our history back to the first moments of existence itself. And we did it through nothing more than careful observation, rigorous thinking, and relentless curiosity. No mysticism, no revelation. Just human beings asking questions and refusing to give up until they found answers. That should inspire you. Because it means that you too have that capacity. You might not become a physicist or an astronomer, but you can approach the world with that same spirit of inquiry. You can look at things that seem mysterious and ask, how does this really work? You can question assumptions. You can seek deeper understanding. The universe is vast and ancient and complex, but it's not beyond comprehension. It operates according to laws we can discover. It speaks a language we can learn. And every time we uncover another piece of the puzzle, we're not just satisfying curiosity, we're connecting with something fundamental about existence itself. Gravity shaped the universe. It formed the first stars from primordial hydrogen. Those stars forged heavier elements and scattered them through supernovas. Gravity gathered that enriched material into new generations of stars and planets. On at least one of those planets, maybe many more, life emerged. And eventually, that life became conscious, became self-aware, began to wonder about its place in the cosmos, and here you are, made of atoms forged in dying stars, standing on a planet held together by gravity, orbiting a star held in fusion by gravity, in a galaxy bound by gravity, in a universe shaped by gravity. And you've just spent time learning that gravity isn't even a force. It's the geometry of space-time itself. You're a temporary arrangement of stardust given the gift of consciousness, using that consciousness to understand the very forces that brought you into being. That's not just science, that's poetry, that's meaning. So when you go about your day tomorrow, remember this. When you feel the ground beneath your feet, you're feeling the electromagnetic force preventing you from following your geodesic through curved space-time. When you look up at the moon, you're seeing an object in perpetual freefall following the contours of Earth's gravitational field. When you check your phone for directions, you're relying on satellites that account for relativistic time dilation to give you accurate positions. The universe isn't separate from you. You're not an observer standing outside looking in. You're part of it. You're made from it. You're a way for the universe to know itself. And now you know a little more about how it works. The journey doesn't end here. There's always more to learn, more mysteries to unravel, more questions to ask. The nature of dark matter, the origin of dark energy, the correct theory of quantum gravity, what happened in the first instant of the Big Bang, what lies at the center of a black hole, whether we're alone in the universe, how life began, where consciousness comes from. These are the questions that drive us forward. And maybe, just maybe, you'll be part of finding some of the answers. Or maybe you'll inspire someone else who will. Or maybe you'll simply live your life with a deeper appreciation for the magnificent, bewildering, beautiful cosmos we inhabit. Either way, you're different now than you were at the start of this video. You see gravity differently. You understand space-time differently. You appreciate the universe differently. And that's worth something. That's worth everything. If this exploration has sparked something in you, curiosity, wonder, a desire to learn more, then I've done my job. And if you want to continue this journey, if you want to keep exploring the deepest questions about reality, then subscribe to this channel, hit that notification bell, share this video with someone who might find it fascinating. Leave a comment with your thoughts or questions. Your engagement genuinely helps this content reach more people, helps more minds encounter these ideas, helps keep the conversation going. Because ultimately, that's what matters. Not just that we learn, but that we share what we learn. Not just that we understand, but that we inspire others to understand. Not just that we explore, but that we invite others along on the journey. The universe is waiting. There are black holes to observe and gravitational waves to detect and mysteries to solve. There are telescopes to build and experiments to run and theories to test. There are students to teach and minds to inspire and boundaries to push. And it all starts with curiosity, with wonder. With the simple decision to look up at the stars and ask, how does this work? You've taken that step today. You've invested your time and attention in understanding one of the fundamental forces shaping reality. That's not a small thing. That's a connection to the entire history of human inquiry. That's a link in the chain stretching from the first humans who looked up at the sky in wonder to the scientists of tomorrow who will unravel mysteries we can't even imagine yet. Thank you for being here. Thank you for caring. Thank you for seeking to understand. The universe is a little less mysterious today because you decided to learn about it, and that matters more than you might think. Keep looking up. Keep asking questions. Keep seeking understanding. The cosmos has so much more to teach us, and we've only just begun. Until next time, remember, you're not standing still on solid ground. You're surfing through curved space-time at hundreds of kilometers per second, following a geodesic through the universe, part of a cosmic dance that's been unfolding for 13.8 billion years, and now you know why. Thanks for watching.